and another all other things are same. The isotopic fractionation factor, starting from the isotopic fractionation factor to the usage and the variations in various deposits or mean oceanic water, anything you can say. The oxygen and hydrogen isotopes vary equally. Okay, so today we'll study about the carbon isotope. So starting from the radioactivity, carbon has three isotopes. Okay, C12, C13, and C14. Okay, three isotopes. Huh? Okay, so sorry. Carbon has three isotopes: C12, C13, and C14. Okay, so C12 you generally know everything everywhere. C12 is present, and the non-naturally occurring C12. Okay, all are naturally occurring, but C12 is generated in nature due to normal processes. Okay, and C13 also same like C12, but C14 is actually not generated in normal process in nature. It generated due to the cosmic action. Okay, we can say cosmic action. When nitrogen 714 is hit with a neutron, okay, then it produces a C614 plus a hydrogen. Okay, so when nitrogen is exposed to cosmic radiation, then it is hit by a neutron particle. Okay, when a neutron particle is hit, then it decays to C614 and releases a hydrogen atom. Okay, in this process, C614 is brought into the nature. Now, what happens? C614 is radioactive in nature. Okay, why? You know the simple rule, uh, the proton by neutron ratio, the neutron by proton ratio, neutron by proton ratio. Okay, the neutron by proton ratio. So here, how much of neutron is there in C614? Anyone? 7, 8. So there are 8 neutrons and 6 protons. So 8 by 6, it will calculate 8 by 6, it will come up to 4 by 3, 1.3, 1.33. So in general considerations, we say that when neutron by proton ratio is greater than 1.2, it is radioactive. It is radioactive in nature. Okay. When neutron by proton ratio is greater than 1.2, it is radioactive in nature. In general considerations. Okay. So in case of C614, it is radioactive in nature. So what happens after formation of C14, the 14 carbon isotope? Okay, 14 carbon isotope, it rapidly mixes with the atmosphere. Okay, it rapidly mixes with the atmosphere along with the normal C612 and C613. Rapidly mixes with the atmosphere and maintains an equilibrium. Okay, maintains an equilibrium. That means it comes into an equilibrium with C614, C613, C612. Okay. Now the plants. Okay, plants. They consume CO2. They consume CO2 to produce food. No, they consume CO2 to produce food. Now this CO2 may be this C may be C12, maybe C13, maybe C14. Okay, so as C14 has already acquired the equilibrium with C12, C13, so in this CO2 part, plant will also consume the C14. No? So now the C14 came into the food. Now food is now taken by all other organisms. No, and after the death of the plants, the bacteria and the other decomposing organisms, they also consume this C14. So now C14 is present everywhere, but C14 is maintaining an equilibrium due to what? Due to the organisms continuously consume C14. No, they वो लोग consume कर रहे हैं continuously C14. But after that, they stop consuming C14. After that, they cannot consume C14 or any kind of carbon. They cannot consume that. So after that, C14 starts to decay. So C14 is decay to what? Anyone? Plus which particle will be released here? Anyone? Beta, beta minus exactly. So beta minus decay will be there, and an antineutrino will be released. Okay. So nitrogen will be formed. Now, if we know the original composition of C14, that is N0, or we can say that is C0, then we can calculate the age of the organism after death. After death, how much time has elapsed? Okay, we can calculate. So the general decay equation, we can say the general decay equation, law of radioactivity. N is equal to minus lambda t or lambda t? Lambda t. Okay, C is equal to C0 e to the power lambda t, the minus lambda t. Minus lambda t. Okay. Check once that is minus lambda t or lambda t. Okay. So this is the decay equation. Okay. So now this is the decay equation. Now what happens? We normally can calculate the C14, the original C14 composition, and then we can calculate the age of the organism. And the problem is we have to calculate the original C14 composition. But after, that is an effect, okay, that is an effect called Swiss effect. Swiss effect. Okay, what is Swiss effect? There is there was a scientist, Swiss. He said that he or she, I don't know, is he or she. So said that gave a theory actually that after 19th century, the production of carbon is multiplied exponentially. No, due to industrial revolution. Due to industrial revolution. तो इंडस्ट्रियल रिवोल्यूशन हो गया तो जो नॉर्मली नेचुरली जो कार्बन प्रोड्यूस हो रहा था हम लोगों ने क्या किया उसको बहुत ज्यादा बढ़ा दिया तो जो जिस जगह में साल में 10 कार्बन निकल रहा था उस जगह में हम साल में 100 निकाला ओके सो इट प्रोड्यूस मोर एंड मोर कार्बन देन इट नेचुरली is being producing okay. So now this equilibrium C12, C13 and C14, this equilibrium is disturbed. No, when C14 is created by the neutron action with nitrogen, okay, then the C12 is being producing simultaneously in nature, but we have anthropologically produced C12 and C13. Okay, and we have also used the fuel, fossil fuel. Okay, fossil fuel. In fossil fuel, there is also C14, some amount of C14. Now, there is a disequilibrium. Okay, so to maintain this disequilibrium, we have to check the isotopic fractionation factor. Isotopic fractionation factor. Okay. So isotopic fractionation factor, depending on isotopic fractionation factor, we use the C14 calculation. Okay. Then this isotopic fractionation factor also useful in various ways, like in petroleum basins. Okay, we'll study about that. What in what areas this isotopic fractionation factor is used. So isotopic fractionation factor is del C13. Okay, del C13 is equal to C13 by C12 sample minus C13 by C12 standard divided by C13 by C12 standard into 1000. Okay, into 1000. This is described in per thousand. This symbol. Okay, per thousand. Oh, this is the isotopic fractionation factor of carbon. And what is the standard for it? Anyone? No, no, small. Small. Previously we are using small, but now we are using PDB. Okay, PDB. The standard for C13 is PDB. PDB. What is PDB? P D belemnite. Okay, P D belemnite. So you know belemnite. What is a belemnite? What is a belemnite? Anyone?
Gastropod fossil.
Anyone? ବେ ତୁ ଶ୍ରୀପତି କୋଉଠି ଅଛୁ କି ବେ? କ୍ଲାସ୍ ଆସିବୁନି ନା କଣ? ହାଁ? ଏତେ ଲେଟ୍ କଣ ତୋର ହଉଛି? So belemnite is a cephalopod, okay? It is not a gastropod, it's a cephalopod. Cigar shape. No, like this. Okay. So PD belemnite. So what is PD? PD is a formation. Okay, it is formation like lithological unit. It is a formation of Cretaceous of South Carolina. Okay, South Carolina. So PD is a formation of Cretaceous of South Carolina. In South Carolina, there is a formation of the age Cretaceous. We named PD formation. We have found a belemnite over there, and we have calculated the 13 by 12 ratio in that belemnite. Okay, so that is called as standard PDB. Then this is calculated by the University of Chicago. Okay, so it is also called as University of Chicago standard. Okay, clear, everyone? Okay, see. So C14 is a radioactive isotope of carbon discovered by Gross. Okay, it is discovered by Gross in 1934. Okay, and its half-life is calculated by Curie. Okay, not that Marie Curie, it is another Curie. And C14 is produced by this process, neutron bombardment with nitrogen. I have already told about this. Okay, then photosynthesis happens and carbon gets an equilibrium state with all of the organisms, living organisms in the earth. Okay, this is the age calculation and this is the Isotopic abundance. Okay, isotopic abundance. C12 is almost 98.89%. C13 is 1.11%, and C12 is almost minus 10 to the power 12, 10 to the power minus 12%. Okay, that means very minute fraction. There is a very minute fraction of C14. Okay, so its half-life is 5730. So conditions, you know all the radioactive conditions. What are the major radioactive conditions which is applicable for all radioactivity? It should be a closed system, no? It should be a closed system. There should not be added any uh, outer carbon after the death of the animal. Okay, so it is not possible after the death of the animal because the animal is not alive, so it will not consume any carbon. Okay, so in case of radioactivity, always the system should be closed. Okay, that's why in uranium thorium there is what concordia and discordia because it deforms. No, easily. So isotopic fractionation. Okay, then we have the Swiss effect. Swiss effect introduction of more CO2 in the 20th century than 19th century due to industrial development. Okay, PD formation, University of Chicago standard. Okay, Bellem. So the name of the fossil is Belemnitilla americana. Okay, the name of the fossil is Belemnitilla americana. The species and the genus. Okay, so PD formation from Cretaceous of South Carolina. Okay. So now the usage of carbon fractionation factors. So this is like a reading thing. So I don't think this is anything to make you understand. Okay, you just have a look. Okay, in case of modern plants, when you analyze for carbon fractionation factor, it is came out to same with the coal fractionation factor. When we analyze the coals, so it indicates that the coals are formed from vegetation. Like that, if we analyze petroleum for this C13 factor, then we will find out that which from which organism this petroleum is formed. Okay, based on organism, there is difference between their consumption habits. नो अलग अलग ऑर्गेनिज्म क्या करते हैं उनका कंजप्शन हैबिट अलग अलग होता है तो उसी के हिसाब से कार्बन का भी फ्रैक्शनेशन फैक्टर वेरी करेगा तो अगर हम लोग पेट्रोलियम के उसका C13 का फ्रैक्शनेशन फैक्टर मेजर कर दिए ठीक है मेजर करने के बाद क्या किए हम देख लिए कि फोरामिनिफोरा है या फिर ऑस्ट्राकोडा है कौन सा ऑर्गेनिज्म से पेट्रोलियम बना हुआ है तो वो हमें मिल जाएगा तो हम लोगों को पता चल जाएगा कि ये लिविंग ऑर्गेनिज्म के जो है वहां से बना हुआ है और कौन सा ऑर्गेनिज्म से बना हुआ है नहीं okay so here it is written how much of variations are there between the carbon del C13 standard value to other values okay like del 13C values for petroleum are uniform with an average minus 28 per thousand of pdb okay so pdb से minus 28 per thousand वेरी करता है ये वैसे ही सब कुछ लिखा हुआ है ओके वैसे ही सब कुछ लिखा हुआ है यहाँ पर जस्ट गो थ्रू इट एंड रीड वंस ओके यू विल अंडरस्टैंड देयर इज नथिंग मच टू मेक यू अंडरस्टैंड सो देयर आर थ्री आइसोटोप ऑक्सीजन ओ 16 16 17 एंड 18 ओके so oxygen combined with hydrogen to form water no oxygen combined with hydrogen to form water then this oxygen can be oxygen 16 can be oxygen 17 can be oxygen 18 but the main thing is this varies with the temperature you already have studied somewhere or you have uh, gave any many examinations where it is written where the questions are there, which of the following isotope is best for paleothermometry? Okay, so oxygen is the best isotope for paleothermometry because oxygen isotopes are very sensitive to temperature. Okay, we'll study about that. So what happens? See, now there are two isotopes, considering two isotopes, oxygen 18 and oxygen 16. Which of one is heavier one? Oxygen 18 definitely. Okay. Now there is water. Okay, now there is water. In water there is oxygen 18, that means H2O 18 and H2O 16. Okay, now I will heat it. Okay, I will heat it. What do you think? This will vaporize? No, this is vaporized. So which of the isotope will go to the vapor? Will try to tend to fractionate to the vapor. Oxygen 16 because it is the lighter. It is lighter one. Okay, it is lighter one. So lighter one will go to the vapor stage. Oh, so these are very oxygen 16 and 18 are very sensitive things. Very sensitive to temperature. Okay, so oxygen 16 tends to fractionate to the vapor state, and oxygen 18 tends to fractionate to the liquid state. Now, if we will consider liquid and I am freezing it, ice is forming. Then which isotope will come to the ice? Oxygen 18. Okay, oxygen 18 will be enriched in ice, and liquid will be depleted in oxygen 16. Right? বুঝি না? So this measurement helps us to find out the temperature. Okay. So considering the oxygen isotopic fractionation factor like that same equation. Okay. Del oxygen 18 is equal to oxygen 18 by oxygen 16 sample minus oxygen 18 by oxygen 16 standard by oxygen 18 oxygen 16 standard. Okay, standard into 1000. Okay, in 4000. Okay, this is the isotopic fractionation factor of oxygen. Sorry, isotopic fractionation equation, not factor, equation. Okay. Then there is a isotopic fractionation factor for oxygen, that is R, or it is called as alpha. Alpha is equal to RL by RV. Okay, RL by RV. What is RL by RV? RL by RV is the del L 18 O18 by del V O18. Okay, that means this del isotopic fractionation of oxygen in liquid divided by in vapor. Understood? Or anything confusing? This is the isotopic fractionation factor alpha. Okay, alpha 18. You can say alpha 18. Isotopic fractionation factor. Okay, this indicates what isotopic fractionation factor indicates how much of enrichment in oxygen 18 is there. Okay, in which state? Liquid state or vapor state? It is obvious that liquid state will be enriched. This thing helps us find out the temperature actually. This thing varies. This thing varies with the temperature. So we'll go to the slide. Okay. So oxygen 16 has a higher vapor pressure than oxygen 18. water vapor formed by evaporation of liquid water is enriched in oxygen 16 and the remaining water is enriched in oxygen 18. Okay, so I have forgot about the standard. The standard is small. Okay, small. Standard is small. Standard mean oceanic water. Okay, standard mean oceanic water means we have to take some samples from the ocean and we have to analyze the oxygen 18 by oxygen 16 ratio there, and that will be the standard. Okay, as ocean is a very vast reservoir of oxygen and H2O, so its isotopic ratio, that is small, it varies very less. अगर एक चीज बहुत ज्यादा बड़ा हो जाए तो उसमें छोटा इम्पैक्ट दिखाई नहीं देता, ठीक है। जो चेंजेस होंगे बहुत माइन्यूट चेंजेस होंगे, बहुत माइन्यूट। ओके, इन द मिलियंस बिलियंस टाइम्स छोटा होगा उसको, तो उसको कंसिडर किया नहीं जाता। नहीं, जब रेडियो एक्टिविटी में जब हाफ लाइफ बहुत ज्यादा हो जाता है तब हम उसको स्टेबल काउंट करते हैं। वैसे ही ऑक्सीजन इज द फास्ट रिजर्वर ऑफ ऑक्सीजन, तो जो वेरिएशन होगा बहुत कम होगा, तो उसको कंसिडर नहीं करते। तो एक बार मेजर कर लिया तो कर लिया, बस निकल गया, ठीक है। तो स्मो इज द स्टैंडर्ड फॉर oxygen fractionation. Okay, so this is the fractionation equation, and there is another standard, National Bureau of Standard USA, also it is followed, NBS is also followed, but there is a simple relationship between NBS and SMO. Okay, NBS and SMO, that is this is SMO is equal to, sorry, उल्टा लिखा है ये, ओके। हाँ ठीक, ओके ओके, ठीक है, दिस इज इक्वल टू, ओके ठीक है। तो स्टैंडर्ड इज इक्वल टू स्मो इज इक्वल टू 1.008 NBS minus 1. Okay, NBS is the National Bureau of Standard of USA. So USA NBS follows another value. So the relationship between SMO and NBS is given here. That is SMO is equal to 1.008 NBS minus 1. Okay. So another thing, del 18O, if del 18O is positive, then it will indicate the enrichment of the sample in oxygen 16, 18 exactly. So oxygen 18 will be enriched if it is positive. If it is negative, the sample will be enriched in oxygen 16. Like that, carbon 14 in case of carbon 13, the del C13 value is, if the del C13 value is positive, then it will be enriched in 13, and if the negative, then it will be enriched in 12. Okay. Boring is usually. এটা কোনো কাম্য করনি এটি। See this one, okay, this is the isotopic fractionation factor, liquid by vapor. When we plot this one, when we plot what, alpha 18 with respect to temperature, so we find this curve, this one, this curve. Okay, the second curve is for deuterium. Okay, I have said that hydrogen and oxygen, all two isotopes are same. You can just replace the isotope values. Okay, all other things are same. So okay, this is the fractionation factor, alpha 18. Alpha 18 is liquid by vapor. Liquid by vapor. So this is the values. Okay, these are the values, and we have plotted against the temperature. See, this is 0, minus 20, plus 20, plus 40, plus 60, plus 80, plus 100. So with increase in temperature, the alpha 18 value decreases. Highest is minus 21.0140. Okay, then it continuously decreases. Okay, so write down with increase in temperature, the isotopic fractionation factor of oxygen decreases. Okay, so if we will have this graph, okay, we will have this graph. We already have this graph, and we have measured the isotopic fractionation factor. Then we can say the temperature. This one will be the temperature. Nah, this is very easy. Okay, so okay, these are other things. There are other things. Let me tell you. So when water vaporizes, oxygen 16 go to the cloud. Okay, so the cloud is now enriched in 16. Okay, now it will rain. So when it will rain, which isotope will come down? Oxygen 18. Okay, not when water vaporizes, not only oxygen 16 goes. The amount of oxygen 16 goes is much more than oxygen 18. But when it rains, the maximum amount of isotope is oxygen 18. नहीं कि oxygen 18 ज़्यादा होगा जहाँ पर rain होगा. So the cloud is continuously getting enriched in oxygen 16. जितना कंडेंसेशन हो रहा है उतना ऑक्सीजन 16 एनरिच हो रहा है कहाँ पर? क्लाउड में, क्योंकि ऑक्सीजन 18 नीचे आ रहा है कंडेंसेशन होने के बाद. सो आफ्टर हायर कंडेंसेशन, जब अरे ये कौन कहती बुढ़ाटा को तो आप पत्थरटा कौन कहते hell. After higher concentration condensation, when hail forms, okay, we'll study about the hail in oceanography atmospheric. Hail, HIL, 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 sorry, my bad. So after almost very high condensation, when hail forms, the hail is solid. It should be enriched in oxygen 18, but it is enriched in oxygen 16 because the cloud is already depleted in oxygen 18 due to rains. No, everyone understood what is the relationship between cloud and rainfall and hail. Okay, this is a simple thing. It comes in the prelim questions. Okay, objective type questions, particularly in NET. So you have already taught about the relic fractionation, na? Relic fractionation. Relic fractionation is also applicable in oxygen fractionation. Okay. This see this R by R0 is equal to F to the power alpha minus 1. Okay, in relic fractionation you have studied Cl by C0 is equal to F to the power D minus 1. Na? D minus 1, 1 minus D. 1 minus D. Okay, F to the power 1 minus D. Like that, this is also a fractionation factor for oxygen. Okay, oxygen, the R is remaining vapor. Okay, considering this is liquid and it is vaporized. Now cloud formed and rain fall. Okay, rain fell. Now R is the remaining amount of vapor. Voila. D minus 1, D minus 1, 1 minus F. D minus 1, ठीक है, D minus 1. D minus 1, okay. जब भी F होता है तो 1 minus F होता है क्योंकि F is a fraction. Okay, F is a fraction, so F is always subtracted from 1. So D is not a fraction, so 1 is always subtracted from D. Okay, I have memorized like that. Okay, so So R by R0 is equal to F to the power alpha minus 1. So R is the remaining vapor. Okay, like Cl by C0. We have studied Cl is the liquid, so C0 is the solid. Na? So how much of fraction is melted? Then you have to calculate that what is the ball distribution coefficient, or what is the fraction of melt produced. No. So R is the remaining vapor. R0 is the vapor before condensation, that is original. R0 is the original. Okay. F is the fraction of vapor that is condensed, that is fell through rain, and alpha is the factor, what fractionation factor. Okay, like batch bond distribution coefficient, same thing. So you can also apply it in the oxygen isotope. Okay. Okay, moving to paleothermometry. How paleothermometry is measured? So paleothermometry is basically measured in CSIR-NET. Okay, CSIR-NET, calcium carbonate. So when calcium carbonate forms, after that it reacts with, also simultaneously it is reacting with the water. Okay, what happens? See, CaCO3 16. Okay, this O is 16. It reacts with H2O 18 and gives CaCO3 18 plus H2O 16. It exchanges the oxygen with water. Okay, the carbonates in ocean, or you can say any formation where paleothermometry can be done. Okay, it exchanges oxygen 16 and oxygen 18 with water. Okay, now this carbonate, it is used for cell formation of the organisms, like corals, you can say foraminifera, or radiolaria. Radiolaria is siliceous, foraminifera is carbonaceous. So all the carbonaceous organisms, they use the carbonates present in the carbonate ion CO3 2 minus ion, or HCO3 minus ions. They use these carbonate ions to build their cell. Now this oxygen 18 is in their cell. So there is variation. Oxygen, the oxygen can be of oxygen 16 or can be of oxygen 18. If we will measure the equilibrium constant of this thing, what will the equation? K is equal to H2O 16, okay, into CaCO3 18 by H2O 18 into CaCO3 16. Okay. So this will be the formula for equilibrium constant of this reaction. It would have भूल हो चाहिए. 1 by 3 CaCO3 or 1 by 3 CaCO3. So in when calculating equilibrium constant, we have to make it the power 1 by 3 and 1 by 3. Okay. So we have to rearrange this. Okay, we will rearrange this. We will rearrange this. How we will rearrange? So we will take CaCO2 to the top and H2O to the bottom. Okay. So the equation will be K is equal to CaCO3 18 by CaCO3 16 divided by H2O 18 by H2O 16. Okay, I have just rearranged the equation. Now what this equation indicates? It indicates the oxygen 18 by oxygen 16 in carbonate by oxygen 18 by oxygen 16 in water. ना समझ में आया सब लोगों को कैसे हुआ ये चीज? किसी को डाउट है? So this thing indicates this. The oxygen 18 by 16 in carbonate, oxygen 18 by divided by oxygen 18 by 16 in water. This thing indicates, don't don't make it equal. Okay, this thing indicates only. This thing indicates. Don't make it equal. So now this is called as, consider this is RCA and this is RH2O. Okay, RH2O. So R means we have already know, R means O18 by O16. Na? Alpha is equal to RL by RB we have calculated. So RCA CO3, you can say RCA CO3 by RH2O. Now this value is highly variable with temperature. You already have known that alpha is variable with temperature. We have seen the graph. So for this value, what happens? We measure the paleothermometry in oceanography from fossil shells only. No? So this value is constant at 25 degrees centigrade, something like 1.008 or what, I'll see. I don't have the value in my mind. Okay. So this value is constant at 25. This the value of this equation is something 1.008 at 25 degrees Celsius. Like that, when temperature decreases or increases, this value is decrease or increase. So if we will measure this value, we can find out the temperature. So let us take a foraminifera cell. Let us take out the carbonates and calculate the OH18 by OH16 value. Okay. Then we can put it here. Then I will find the ratio. After finding the ratio, I can directly find out the temperature, or I will put the approximation factor in the graph. Okay. So this value is 1.0286 at 25 degrees centigrade. Okay. For RCaCO3 and R water, this is 1.0286 at 25 degrees centigrade. So this fractionation is temperature dependent. Okay. C, we take the small because it is not affected because of its huge amount. This is written only. So सबको पता चल गया कैसे हम लोग पालियोथर्मोमेट्री करते हैं सेल में से. या किसी को डाउट है बोलो. Like that, the oxygen is in hydrothermal ore deposits. You just go through this. Okay, there is nothing much more to make you understand. So you just go through this. I'll upload the notes today only. The notes for so like that you can write the equation for sulfur. No, the fractionation equation. Okay, the del S 34 value, del S 34. So sulfur has also 3 isotopes. 32. No, sulfur has 5 isotopes. 5 isotopes. 32, 34, 35, 36, 37. 5 isotopes. Sulfur has 5 isotopes. So fractionation factor, fractionation equation is this. Sorry, isotopic composition is this. Del S34 is equal to sample del S34 by 32 minus 34 by 32 standard by standard into 1000. Okay, per 1000. So this is the isotopic composition, and the standard is, what is the standard for a sulfur isotope? Canyon Diable. Okay, Canyon Diable. So this is a meteorite. The name of the meteorite is Canyon Diable, and this Canyon Diable we find the mineral troilite. Okay, troilite. Composition of this troilite is FeS. Okay, FeS. So the standard is the troilite. Okay, the S32 by S34 by S32 value in FeS, that is troilite in Canyon Diable meteorite of Arizona, maybe. Let me check this. It is found in Arizona. Okay, Arizona. Okay, Arizona. So the value of S32 by 34. Okay, mark this. S32 by 34 is 22.22 in this meteorite. Mark this. S32 by 34. But when we measure this, we measure 34 by 32. Okay. Mm-hmm. Okay. So sulfur 34 and 32 variation is much more dependent and only dependent actually on the bond strength. Okay, on the bond strength. So sulfur 32 bond with oxygen is very weak and sulfur 34 with oxygen bond is very strong. Okay, so when fractionation occurs, the sulfur 32 oxygen bond is easily broken and sulfur 34 oxygen bond is not easily broken. Almost enriched in more than 20 to 30%. Okay, particular value should be written in coming slides. So S32 oxygen is much more prone to weathering or much more prone to breaking. Okay, 20 to 30% more than sulfur 34 oxygen bond. So basically sulfur fractionation occurs due to biogenic causes. Okay, biogenic causes, sulfur decomposing bacteria. Okay, they are known as, their name is desulfovibrio desulfurican. Okay, desulfovibrio desulfurican. So causes of variation of isotopic composition. লেখা আছে টেনশন নাই তোরা লেখা আছে ହେଲା. So causes of variation of isotopic composition. The reduction of sulfate ions to hydrogen sulfide by certain anaerobic bacteria which results in the enrichment of S32 in HS. Okay, what it said? It said that why isotopic composition varies. Okay, we knew that in carbon why isotopic composition varies. In case of carbon, why it varies? Due to Swiss effect. Due to Swiss effect, much more of carbon is produced in 20th century than that of 19th century, after 19th century. Okay. In oxygen, why it is varies? Due to temperature. Okay. Due to temperature. Now, in case of sulfur, why it is varies? Due to two factors. One is biogenic fractionation. So, anaerobic bacteria decomposes SO2 to HS minus. Okay, hydrogen sulfide ion. Okay, now this SO2 to HS minus depends which sulfur. S32 is breaking to HS minus or S34 is breaking to HS minus. That means in this HS minus it is HS32 minus or HS34 minus. Now, this is one and the most important cause. Okay, we study this one only. And another cause is various isotopic exchange reaction between sulfur-bearing ions, molecules, and solids by which sulfur 34 is generally concentrated in compounds having highest oxidation state of sulfur or greatest bond strength. So sulfur 34 is fractionated to highest oxidation state. Okay, this is another cause, but this is not of much more importance. Okay, we focus on only the biogenic fractionation. Okay. So what happens in biogenic fractionation? I have already told you that in the living organisms or in the nature or lakes, anywhere the sulfur is present. Okay, sulfur is present. So the biogenic decomposers, that is for sulfur, desulfovibrio desulfurica. Okay, this is the name of the bacteria. This decomposes SO2 to HS minus. Okay, but the S32O bond and S34O bond, between these S32O bond is weaker. So the first HS produced or H2S produced should be enriched in S32 or S34. 32 because 32 is easily broken. Okay. So the fast H2S produced is 22% more enriched in S32 than that of S34. Okay, if 100 numbers of S34 goes, then 122 numbers of S32 goes to H2S. Okay, this is the basic cause of fractionation. Clear? Okay. Now using this thing, we can analyze very wide number of petrological criteria or paleontological criteria. Okay. So these things are written here. Sulfur, in case of sulfur, there is not much more things. Okay, the simple things. Role of sulfur in petroleum. Actually, the sulfur isotope is widely used in petroleum. Why? Because to identify the trap and the reservoirs. Okay. So the petroleum produced same reservoir will have same del S 1334 वैल्यूज ना. वो एक रिजर्वेयर से निकला है, मतलब एक रिजर्वेयर, मतलब वो क्या हुआ कि एक ही वैल्यू दिखाएगा नहीं, एक ही वैल्यू आएगा. सो नाउ कंसीडर ए सिचुएशन, there is a litho unit and here there is a petroleum reservoir and there is another reservoir here. Okay, we have this we have tapped this reservoir and we are generating oil. Now what happens, we also tap sidewise. Okay, in petroleum exploration. तो क्या हुआ, एक ऑयल में S34 का डेल S34 का वैल्यू अलग आ गया, तो उनको क्या इंडिकेशन मिलेगा, शायद और एक रिजर्वेयर है आसपास में. हम लोग जो जिस रिजर्वेयर से निकाल रहे हैं वो रिजर्वेयर नहीं है, ये दूसरा रिजर्वेयर है. ठीक है, इसमें हेल्प करता है क्या, सल्फर आइसोटोप. ओके. तो सल्फर पेट्रोलियम में क्या हुआ, वो क्या होता है, H2S गैस इज कंटिन्यूअसली एमिटेड. तो ऐसे ही सल्फर इन कोल. ओके, बाकी चीज जैसे लिखा हुआ था ऑक्सीजन में, कार्बन में, वैसे ही लिखा हुआ है. सब लोग देख लेना, मतलब इसको थोड़ा पढ़ लेना, ज्यादा कुछ लिखा नहीं है, बस स्ट्रेट थिंग्स आर रिटन. स्ट्रेट थिंग्स आर रिटन, देयर इज नो कॉम्प्लिकेटेड थिंग्स हियर. ओके, सल्फर इन कोल, सल्फर इन सल्फाइड ओर डिपॉजिट्स. ओके, स्ट्रेट थिंग्स आर रिटन, बस इसको रीडिंग मारना है. ओके, रीडिंग मारना है और समझ थोड़ा उसका जो थीम याद रखना है. ठीक है, सब कुछ याद नहीं रखना है, थीम याद रखना है कि क्या बोल रहा है सल्फर आइसोटोप, किसमें यूज आ रहा है. ये वैल्यूज याद रखने की जरूरत नहीं है तुमको. बस जीएसआई में क्वेश्चन आया कि सल्फर आइसोटोप का सल्फाइड ओर में क्या रोल है, सल्फाइड ओर में और डिपॉजिट में क्या रोल है. तो तुमको लिखना है कि हम लोग देखेंगे कि हाइड्रोथर्मल और डिपॉजिट है कि हाइड्रोथर्मल, फिर इग्नियस और डिपॉजिट है कि कैसे हम लोग पता लगाएंगे. फिर इग्नियस सोर्सेस जो होता है, इग्नियस सोर्सेस का नैरो रेंज होता है, हाइड्रोथर्मल सोर्सेस का वाइड रेंज होता है, ये सब लिखा हुआ है. बस यही चीज लिखना है, वैल्यूज लिखना नहीं है. ओके, सबको समझ में आया है, मने भी रहो नहीं जैसे. तो सबको समझ में आया या किसी को डाउट है बोलो.